Section: Introduction. In this section, we delve into the realm of reinforcement learning from human feedback, RLHF. RLHF plays a crucial role in the success of popular large language models, LLMs, like OpenAI's and Anthropic's Claude. The key strength of RLHF lies in its ability to incorporate human values and preferences into language models effectively, without the need for explicit reward specifications. Central to the RLHF process are reward models, RMs, which are created by training copies of the original language model on labeled preference data. These RMs can predict user preferences between different pieces of text. Subsequently, a reinforcement learning optimizer utilizes the signal from the reward model to enhance the original model's performance across various tasks. While much attention has been given to the post-RLHF model, known as the policy, and the pre-trained model, the fundamental aspects of the RLHF process have not received adequate scrutiny. Evaluation of reward models is crucial for understanding the efficacy of RLHF and how human values align with language models. Recent efforts have focused on training reward models, but the evaluation has been limited by the use of validation sets from previous RLHF training processes, which have accuracy limitations due to inter-annotator disagreements. Our work aims to address this evaluation gap by introducing RewardBench, a toolkit designed for benchmarking reward models. RLHF is a versatile process used to enhance specific and general capabilities of language models, such as safety, reasoning, instruction following, and steerability. Evaluations of reward models need to encompass all these aspects. We have curated new data and repurposed prompts from various LLM evaluation toolkits to create structured comparisons across different reward model properties. These comparisons vary in difficulty, with some prompts allowing many reward models to achieve high accuracy, while others pose a challenge even for state-of-the-art language models. Additionally, we aim to map the landscape of available reward models through a reward model leaderboard. We evaluate various models, including classifiers like Ultra-RM, Starling, Pair-RM, Steam SHP, and models from Reward-Ranked Fine-Tuning, RAFT. We also assess popular chat models trained with Direct Preference Optimization, DPO, to shed light on the strengths and limitations of different RLHF methods. Through RewardBench, we provide a standardized framework for evaluating diverse reward model architectures, along with tools for visualization, training, and analysis. We release all data used in the evaluation to facilitate further analysis of reward model properties. Our work highlights the differences between DPO and classifier-based reward models across different datasets, charts the current state-of-the-art reward models, and showcases the limitations of existing preference data test sets. Ultimately, we aim to advance reward model training, deepen the scientific understanding of integrating human preferences into LMs, and foster the development of better aligned, open language models. Section Summary. In this section, we introduce reinforcement learning from human feedback, RLHF, a crucial but underexplored tool behind the success of large language models like OpenAI's Claude. RLHF leverages reward models trained on labeled preference data to improve language models by predicting user preferences. We address the lack of evaluation techniques by presenting RewardBench, a toolkit for benchmarking reward models, aiming to enhance the integration of human values into language models and improve their alignment with user preferences. Section: Reward Model and RLHF Evaluation. In this section, we evaluate preference-tuned models using various frameworks like Alpaca Farm. In Alpaca Farm, we use language models, LLMs, to simulate human preferences by comparing model outputs with reference model outputs. The evaluation metric is the win rate of the model over the reference model based on 805 instructions. Similarly, MT-Bench evaluates chatbots on multi-turn conversations judged by LLMs as proxies for human judgments. Chatbot Arena is an evaluation benchmark that gathers preferences between two different model outputs through crowdsourcing. These evaluations do not directly assess the reward model. On the other hand, some studies focus on analyzing the reward model. For example, some researchers examine the training dynamics of reward models and find a strong correlation between output length and rewards. Another analysis looks at reward inconsistencies by creating a benchmark of contrasting instructions. Importantly, they discover that reward model inconsistencies also impact the training of reward learning from human feedback, RLHF, and the resulting model. The first step in training a reward model for RLHF is collecting preference data from human labelers. Individuals are presented with prompts, questions or tasks, and asked to choose between completions. The data is transformed into prompt-chosen rejected trios for training the reward model. Training involves a classifier predicting human preference probabilities between two answers using a Bradley-Terry model. The reward model parameters are estimated by optimizing maximum likelihood loss. For language models, the reward model is often implemented by adding a linear layer for prediction or replacing final decoding layers with a linear layer. During inference, the reward model returns a scalar indicating the probability of a completion being preferred. Direct preference optimization solves the RLHF problem without requiring a separate reward model by directly optimizing the reward function from model probabilities. The RewardBench dataset is designed to evaluate reward models across various metrics like chat, instruction following, coding, and safety. It consists of prompt completion pairs for evaluation, aiming to assess the reward model's ability to assign credit accurately. Each data point includes a prompt, a chosen completion, and a rejected completion, with the reward model scoring each prompt to determine wins based on the model's preference. Accuracy is reported as the percentage of wins in each subset of the dataset. Section Summary. In this section, we evaluate preference-tuned models using downstream evaluations like Alpaca Farm, where language models simulate human preferences by comparing model outputs with reference models. Training a reward model involves collecting human preference data, training a classifier to predict preference probabilities, and optimizing the model parameters. Direct preference optimization solves the RLHF problem without a separate reward model by directly optimizing the reward function from model probabilities. The RewardBench dataset provides evaluations for reward models across various metrics like chat, instruction following, coding, and safety, aiming to assess the model's ability to assign credit to good or bad content accurately. Section: RewardBench scoring. In this section, we focus on scoring the RewardBench. Our main scoring metric is accuracy. We determine the score the reward model gives for a prompt-chosen pair and a prompt-rejected pair. If the chosen pair has a higher score than the rejected pair, we assign a true label. This process is illustrated in Fig. More scoring details, including for DPO models, can be found in Sec. When it comes to classification as correct or not, a random model would score 50 on our benchmark. Many models perform around or below this random baseline on various subsets, showing significant room for improvement in reward models. To create a single evaluation score that represents all subsets, we calculate a weighted average across results. For most subsets discussed in Sec, except for reasoning, we calculate a weighted average across all prompts in the subset to normalize the section score based on the size of each category. For instance, in chat, we average the Alpaca eval and Mount bench sets based on the number of prompts. In reasoning, we give more weight to the PRM math subset to balance code and math abilities in the final score. For prior sets, we take an unweighted average due to the large differences in dataset sizes. After calculating weighted averages for all subsets, the final score for RewardBench is the average across all subset scores. Moving on to the evaluation results, RewardBench assesses various public reward models with parameter counts ranging from 400 million to 70 billion. These models are trained either as classifiers or with direct preference optimization when the reference model is available. We present the key findings of RewardBench in this section, with additional results provided in the appendix. We specifically examine state-of-the-art reward models, results of models with similar sizes at 7 billion, and the impact of scaling DPO reward models on performance. We delve into the comparison of state-of-the-art reward models. The top 20 models are summarized across different sizes: large, medium, and small. Large models demonstrate consistent high performance on sections like chat, hard, and reasoning, with the model Starling ERM34B leading the pack. Medium-sized 7B models like Starling RM7B Alpha, Zephyr 7B Alpha, and Noose Hermes 2 Mistral 7B DPO also perform well. The small, more accessible models show varying performance levels, with STABLELM2ZEPYHR1_6B and OSIST ERM 2.1 Pythia 1.4B Epic 2.5 as the state-of-the-art models. Performance variations are observed based on the base model size and quality. We also explore the impacts of different base models on evaluation results. We analyze models trained with similar fine-tuning approaches on various base models. Scaling shows improvements for Llama 2 across all sections of RewardBench, while Qwen 1.5 exhibits less consistent improvement and even regression on prior sets. Comparisons are made between different base models and fine-tuning methods using Zephyr class models, highlighting the effects of these variations on model performance across different categories. Section Summary. In this section, we focus on scoring in RewardBench, where accuracy is the primary metric. We determine scores based on the model's preference for chosen prompts over rejected ones, with a random model achieving a score of 50. We also evaluate various reward models across different sizes and highlight the impact of scaling on performance, showcasing the state-of-the-art models in different categories based on their parameter counts. Section: Different shapes of reward functions. In this section, we explore different shapes of reward functions. We observed varying magnitudes and distributions of rewards assigned to different reward models over the RewardBench evaluation dataset. Some reward models have Gaussian scores, some are centered around zero reward, and a few exhibit both characteristics. While current research often focuses on preventing over-optimization in reward models, it is crucial for future studies to determine a practical output distribution for reward models that can be effectively used in downstream reinforcement learning training. When we look at the performance summary in table, we find that current reward models can effectively solve certain subsets of RewardBench, achieving close to 100% accuracy. However, many subsets face challenges such as low performance ceilings or high performance variance. Subsets with low ceilings, particularly in the chat, hard, and reasoning sections, highlight areas where preference datasets and reward modeling methods can be expanded to enhance performance. On the other hand, subsets with high variability, like many of the safety subsets, indicate areas where best practices can be standardized. Comparing different reward models across chat hard categories, as shown in table, is essential for understanding their performance. Adversarial subsets from LLM bar play a crucial role in this comparison as they present scenarios where distinguishing between similar answers is challenging for most reward models. The chat hard section, similar to the prior set section, showcases instances where DPO models outperform other models, even those with lower overall performance like the Qwen chat models. The improvement in performance of DPO models can be attributed to various factors, including better base models and well-aligned training datasets. In the reasoning section of RewardBench, we observe a wide range of performance variations among models, ranging from 35% accuracy to 90% accuracy. The difficulty level in reasoning models surpasses that of adversarially designed data, indicating that reward models can effectively identify known bugs in reasoning or code. When evaluating across safety metrics, as presented in table, we encounter challenges in balancing the model's tendency to refuse responses. Different models demonstrate varying behaviors, with some focusing on helpfulness without strong safety considerations, while others incorporate safety information in their training process. The diversity in model behaviors underscores the importance of using RewardBench as a tool to quickly assess the safety behavior of a candidate model, especially those trained with DPO. Considering the length bias in RLHF and reward models, we structured RewardBench to ensure that chosen responses are either similar in length or shorter than rejected responses. For instance, the alpaca eval length subset aims to differentiate models based on their capabilities while maintaining a similar average response length. Although further statistical tests are required to fully comprehend this bias, the results indicate that many models achieve high accuracy levels, exceeding random chance. Lastly, we acknowledge the limitations of prior test sets used in training popular models with RLHF. Models trained on datasets like ultra-feedback or Nectar often lack publicly available validation sets, leading researchers to compare model agreement with existing test sets from previous RLHF studies. The performance of various models on the prior sets section of RewardBench highlights the need for extensive research to understand the constraints of these datasets fully. Section Summary. In this section, we observe different shapes of reward functions by analyzing the magnitudes and distributions of rewards assigned to various reward models over the RewardBench evaluation dataset. These reward models exhibit varying characteristics, with some being Gaussian in their scores, some centered around zero reward, and few possessing both attributes. While current research often focuses on mitigating over-optimization, future work should aim to determine a practical output distribution for reward models that can enhance downstream reinforcement learning training. Section: DPO models versus classifiers. In this section, we compare DPO models to classifiers. We have observed that DPO-trained LLMs are often used for their generative capabilities, but there has been little research on how they stack up against RMs trained as classifiers. Currently, there are more DPO models available to the public, mainly because DPO requires fewer computational resources and has existing implementations and relevant datasets. Our analysis on RewardBench shows that recent DPO methods perform well, except in the prior sets section. To understand how DPO rewards are calculated, refer to the corresponding section. By using the same inference code from popular DPO training implementations, we can evaluate them as RMs by not backprop-agating gradients through the models. The simplest way to evaluate DPO-trained models requires more GPU memory due to the need to compute rewards from two models simultaneously. However, this can be mitigated by calculating probabilities sequentially over the policy and base models. Some released DPO models lack clear documentation on the reference model used in training, leading to ambiguous benchmarking results. In cases where a reference model is unavailable or computational resources are limited, an alternative approach is to obtain a reference-free reward based on comparing probabilities. Normalizing this reward using different methods is crucial to avoid a length penalty in the loss function. We have experimented with using a wrong reference model, which significantly reduced the performance of DPO-trained RMs to levels similar to a random baseline. There is still much to learn about the best practices for training RMs, such as the impact of training hyperparameters like beta-KL regularization and the number of training epochs. Moving on to generative reward modeling, recent studies have explored using LLMs as feedback mechanisms similar to reward models. While these approaches differ from DPO models in terms of score calculation and prompting requirements, they offer promising avenues for future exploration. Reward models play a crucial role in encoding human preferences or values in the RLHF process. Understanding whose values are embedded in reward models is essential, and further research is needed to investigate this aspect, including studying different base models, fine-tuning techniques, bias amplification in synthetic datasets, and various datasets. Lastly, the concept of safety in or after RLHF is gaining traction, with the shift towards using small models as safety classifiers alongside larger generating models. Evaluating systems with additional safety classifiers separately on specific tasks is crucial for a fair comparison on platforms like RewardBench.